We talked last time about the Knuth-Morris-Pratt algorithm, which turned out to be a worst-case optimal algorithm for string matching. You might remember it had essential running time theta of n plus m, so that's the same as scanning the text and the pattern each once. And that's clearly the best we can do, or can we? What else could we hope for than optimal? Optimal is a dangerous word because it can mean many things. It means best possible, but in what sense? Depends what you compare it with. And Knuth-Morris-Pratt is optimal in the worst case sense. So there's instances of a text and pattern for which you cannot avoid essential n plus m effort to solve the string matching problem. But that does not mean there's not specific texts and patterns, or maybe actually a lot of texts and patterns for which you can do it much faster. And here's an example. Suppose you have a very boring text and also a fairly boring pattern, and they have nothing in common. Now, our algorithm cannot really look at those and see, like we do, that they obviously won't match. But it has to prove by individual character comparisons that there's no match of this pattern in the text. So what could it do? It could lay down the text like this, and then it could make these 4 comparisons, and they would prove to any observer that there's no match of the pattern in the text, because any match would at least have to overline, at least have to match at these positions. But we know that the pattern has always this letter x, and the text at these 4 positions does not have the letter x. So there's no way how I can slide the pattern left and right to make it align. There's always one of those 4 probe positions that kills any possible shift or any possible guess for the pattern. All right. So KMP is optimal in the worst case sense. We cannot always do better, but we might sometimes be able to do better. And here's a specific example, but let's try to be a little more generic about this, a little more general. A core insight, the main insight in Boyer-Moore's algorithm is it's maybe not a smart idea to check the pattern from left to right and also move it left to right. Let's move it from left to right, but check it from right to left. That's exactly what I mean by check from right to left is in the naive algorithm, we arbitrarily choose the first guess, and then we chose arbitrarily to compare this character with the text and this with that, if in case it matches, in case they matched. You continue scanning through the pattern from left to right to check if there's a match. You could do the same thing, but just start on the right and check the matches in that direction. There's no particular reason why one would be better than the other, except that it turns out that doing it from the right can sometimes be much better. As you've seen in this example, sometimes a single comparison rules out more than one guess. You could rule out all the 5 guesses in the example. And we'll see what it means to be lucky in this case. There's also a downside, and maybe a good reason why the earliest algorithms did not do this right to left. If you look at it closely and try to do something that's worst case efficient again, it becomes a little more complicated or more tricky. And that's why, for most part, we'll ignore that. We'll only show a solution like the original Boyer-Moore algorithm. It only goes a certain amount of into the direction of worst case optimality, but it doesn't quite achieve it. So here's a dangerous instance. If the text is boring, it's all A's, and the pattern is all A's except a B at the beginning. The method, if you just naively applied it, always checks the entire pattern, and then, oh shoot, the first character doesn't match. Let's try one shift to the right, because all the other characters matched. So there's no, you cannot easily say that from this mismatch. So, well, let me do a small example for that. If that's the text and it continues, and here's the pattern, you compare right to left, these all matched, but then this one didn't. Now, what can you conclude from this mismatch? Unless you put in more effort, you cannot say that all of those positions also can't be a match. That would need the insight that B is not A, which was the other character. Okay, so this is a bit unclear in argument. But if you do it stupidly, such inputs can be dangerous. You might redo the checking from right to left for every position. So you would definitely like to avoid that. And the original Boyer-Moore algorithm had two rules, two heuristics on how much you can shift your pattern to the right in case of a mismatch. And because I promised I'll speed up a bit on the remaining part of this unit, I essentially just show you the examples for the two heuristics, and you will get some flavor of the algorithm, but we won't do the details, and you're not required to know the details. The first heuristic is called the bad character heuristic, and the idea is as follows. Here's a text and a pattern. We do what we always do in Boyer-Moore. We try to compare the current guess from the right in the pattern, but we immediately find a mismatch. Now the bad character is this R, because that's the character in the text that did not match whatever we found in the pattern. Now R, if you look at the pattern, doesn't occur anywhere in the pattern. So it's a bad character from the perspective of the text. It's a good character from the perspective of the algorithm, because it allows us to entirely shift the pattern beyond the current position. There's no way that aligning the pattern like this or like this or like this will yield a match, because we would always have to match the R with some position in the pattern, but there's no R in the entire pattern, so there's no use to try that. All right? That's a simple idea of the bad character heuristic. Now, to be a little more general, it doesn't always work perfectly. In this case, we compare, again, have the same case. The bad character is the W, and you can shift it to the entire right. In the second example, things are a little more complicated. Okay, we'll finish the comparisons from the right and find that here's actually a match, but that's not as important. The important part is here now. In the second example, we again do the checks from the right. We find our mismatch, and R is the bad character in the text that we couldn't couldn't align here with the E, but there is an occurrence of R in the pattern. So in the general case, what we'll do is we'll take this character that was a mismatch, we shift the pattern as much to the right as we can until the first occurrence of that character aligns with that character, which also means we shift the pattern so that the last occurrence of the bad character is aligned with that position. So in that case, that's only a shift by one position, but in general, it could be more. Now we again have a mismatch here, and the M occurs at the first position, so we can shift it so that the last occurrence of M, which happens to be the first character of the pattern, is aligned with this position in the text. Okay? It's a fairly simple idea, and all you need to compute for that is where in the pattern is the last occurrence of all the symbols in the alphabet. That's a fairly simple trick. And it turns out if you apply this, if the pattern is not very long and the alphabet is fairly large, so standard text files, and you search for a 10-character word, usually this bad character heuristic jumps through the text fairly quickly. we finish off with comparing from the right, and then we find the match. Now, this heuristic is good if we find a mismatch early on. The opposite thing that we would like a good string matching algorithm to do is if it has matched from the right a certain portion of the pattern already, it shouldn't forget all those matches. It should try to make use of this knowledge that it acquired. And there's a second heuristic. So this is how to compute the last occurrence function for the first heuristic. I'll skip that part. The second heuristic takes care of this remembering the matches to a certain extent, at least. So the first heuristic, I guess, is fairly straightforward. This one is a little more intricate. Don't worry too much. But the general flavor is as follows. You have a pattern like this. And, well, you found a certain part where the pattern matches a part of the text. A part of the pattern matches part of the text. The part that matches here will always be a suffix of the pattern because we compare from the right. But then we found a mismatch. OK, the first heuristic would look at this character and try to shift the pattern and so on and so forth. The second heuristic looks at this matched part. And it asks, where does this else occur elsewhere in the pattern? Does it occur somewhere before? And if it does not occur somewhere before in the pattern, we can actually shift behind this. Because we would have to, any match has to have the same characters in these positions. So we can only, it only makes sense to try shifts that align other pattern characters with these match characters. OK, so in this example, we do find the else here. So we would shift the pattern like this. And I'd like to point out that this matched part now is in the middle of the pattern. It's not at the beginning and not at the end. There's stuff before and stuff behind it where we don't know if it matches the text or not. And that's what makes this a little more complicated than the Knuth-Morris spread part, where we always went from the left, and it was always a prefix of the pattern that we've matched. Now it can be anywhere in the pattern in the middle. OK. There's a second case that can also arise. So same situation. We found a certain suffix of the pattern in the text. But this subword food doesn't occur anywhere else in the pattern. Does that mean we can shift the pattern entirely behind this current position? Not in this case, because there's a certain prefix of the pattern that aligns with the suffix of the pattern, or the suffix that we matched. So in the above example, else occurred as an entire occurrence somewhere else before. Now only part of the good suffix occurs somewhere in the pattern. Well, and if that's the case, it must be at the beginning of P. All right? So those two cases, they look similar, but they're a little different in how the shift is done. So that's why they're separate here. In both cases, the idea is you have a certain part of the pattern, a good suffix that you already found in the text. Only try shifts that bring some of those characters at least in alignment with other positions in the pattern. Don't try shifts where this already implies a mismatch. You don't have to try those. All right. This is, again, the two cases explained more closely what exactly is going on. One remark I want to make at this point is it was easy to compute this last occurrence of every character in the pattern. It's not quite obvious how to compute this heuristic, but you can do something based on the COMP failure function. I promised you last time we talked about the failure link automata. And then I said, well, people have used this index. This is array F with an off by one index instead of the fail array that we used. And I claimed the same array occurs in many other string problems. Here's one of those. You can compute whatever you need here, all those details I skipped. You can compute that based on the Knuth-Morris-Pratt failure function. Okay, that's really all I want to say about the Boyer-Moore algorithm. To take away for you is Knuth-Morris-Pratt is optimal in a certain sense. And I'll ask you about that sense in a second. And you can sometimes beat it. And actually, for many typical cases, Boyer-Moore beats it by a fair margin. So depending on the type of text your string matching works on, it might well be the better method, even though the worst case running time of the method I presented, even though we were smart with this good suffix, it's not enough to get the worst case below this trivial bound. There's still bad cases where you check the pattern many times. But even coming up with those bad examples is tough enough. Another interesting fact is if the pattern does not occur in the text, it turns out that the method, like I presented it, is actually linear time, is essentially optimal, n plus m. But the proof that this is true is very complicated. So it's another interesting feature of this algorithm. It looks fairly harmless when you start. Well, just start from the right instead from the left. But there's a lot of intricate things going on. But we won't look at that in detail. Okay. Another little piece of information I want to point out. We did talk about Knuth-Morris-Pratt in detail, so you can understand how this part works. You can modify the Knuth-Morris-Pratt algorithm fairly easily so that it reports all matches of the pattern in the text in the same time. You just keep going with your simulation of this failure link automaton. And you have to make sure that the last state has a proper failure link. But that's easy modifications of the algorithm we discussed. Again, with Boyer-Moore, that's not so easy. All right. Then let's briefly test your understanding on the level I think you should have for this. There you go. Okay, I was a bit slow. So that worked well. Let me go back to the slides. Well, that's exactly the point that we discussed. Knuth-Morris-Pratt is optimal in the worst case, but that's notwithstanding some inputs, Boyer-Moore beats it. That should be Boyer-Moore in each case. It's not BP. It's nothing about gas. Okay, we cannot make any statement in either direction for all inputs. You can find examples where one beats the other in both directions. But if we don't have matches, then this statement from the last slide essentially guarantees us something like this, that Boyer-Moore doesn't do much worse than KMP. All right, that was Boyer-Moore.